Flock Freeform allows law enforcement to search video and vehicle evidence in plain language. Is there a missing person wearing a camo hat with a forest green sweater? Set an alert and get notified once they appear on camera. If you feel like this could be an invasion of your privacy, don't worry. Flock Safety develops license plate reading software to integrate your license plate reading systems with your other license plate reading systems, as shown in this example image. If you've been living under a rock for the past 12 months, you may not have heard about Flock Safety. They work with local businesses and law enforcement to install traffic cameras to help keep communities safe. Because of data sharing agreements between different jurisdictions, these cameras can be used to track vehicles almost anywhere in the United States.
And one of the reasons why is because they're like, hey, we want to have better transparency with how our law enforcement uses technology. We're like, great, we'll build that. I didn't know that was a problem. That wasn't a problem in Atlanta.
The YouTuber Ben Jordan has covered many of the social and technical issues with Flock's surveillance system. However, none of his coverage explains how Flock's AI works once the video makes it to the data center. Ben showed how to use object detection software to search for specific objects, but the software he used doesn't include categories for things like camo hat or forest green sweater. I think we take for granted that AI can magically solve problems, but there's an incredible amount of engineering that goes into the scaling and efficiency of AI systems. To better understand how Flock Freeform works, I built my own version using entirely open source software. In this video, I'm going to explain the technology miracle behind our privacy nightmare. Let's get started. EyesOffCR.org is a grassroots organization dedicated to holding law enforcement accountable in Cedar Rapids, Iowa. They acquired a Flock Falcon Flex camera from eBay in order to reverse engineer how it works. Their blog includes a picture of the internal hardware. The immediate thing that sticks out is this module for NimbeLink Skywire. Skywire is a modem that enables devices to connect to cellular networks. According to Flock's Law Enforcement Customer Implementation Guide, Flock cameras require adequate cellular service using AT&T or T-Mobile to be able to process and send images. Since Flock covers the cost of the cellular connection, they're incentivized to minimize the amount of data being transmitted to the server. Business pricing for cellular service isn't publicly available, but if we use prepaid cellular plans as a proxy, we can reasonably assume that it costs at least $2 per gigabyte of data. To estimate the typical file size for a video, I recorded 2 hours of footage from a busy street outside my friend's house. Extrapolating from the video's duration and file size, the cost of continuously transmitting video from a traffic camera to a server could be as high as $3,000 per year. That's a pretty obscene cell phone bill. A very simple way to massively compress the video is by using motion detection. If nothing is moving, then why bother streaming to the server? EyesOffCR found that Flock cameras include OpenCV on device. OpenCV is likely used to resize the video down to a smaller resolution, then run a motion detection algorithm. This lines up with the Customer Implementation Guide, which recommends placing cameras after traffic intersections to prevent stop-and-go motion activation. Although motion detection eliminates a ton of redundant video frames, it's not that effective on its own. For example, what if rain is blowing directly onto the camera lens? Or what about when the trees sway with the wind? What about when a bird dances around in the grass? All of these cause motion, but the only motion that really matters is the motion of people and vehicles. EyesOffCR found the YOLO Pico 3 Float 16 model on the camera. In this context, YOLO stands for You Only Look Once, which is a machine learning model used for object detection. The likely source for this model is Ultralytics, given that they list Flock Safety as a customer on their website. Because running a machine learning model is fairly compute-intensive, it should only be triggered after motion detection. Video should only be transmitted if the vehicle is actually moving. To test that object detection really does cut down on file size, I ran object detection on my video to filter out redundant frames using the method I described. Filtering the video reduced the duration and file size by about 75%. Keep in mind this was during rush hour traffic. If I had recorded the same street at nighttime, the file size reduction would have been much more significant. As I already mentioned, the YOLO object detector only knows about classes of objects that were explicitly labeled in its training data. How can an AI model say anything meaningful about classes that it's never seen before? This is known as zero-shot learning, and it's where our secret weapon comes in. CLIP, or Contrastive Language Image Pre-training. CLIP was released by OpenAI in 2021 as a tool to link images to text. CLIP is not one, but two different AI models. One model encodes images, the other model encodes captions. During training, a batch of n images and a batch of n captions were encoded using the models. Then, an n by n matrix of similarities was computed. The objective function rewarded similarities between matching image-caption pairs and punished similarities between non-matching pairs. The models were trained on images and their associated captions scraped from websites. The reason CLIP works as a zero-shot image classifier is because of the captions. CLIP may have never seen a cat-wearing suit before, but it knows what a cat looks like, and it knows what a suit looks like, so it can put two and two together, so to speak. Once we've generated CLIP embeddings for an image and a search query, how do we calculate the similarity between them? Each embedding is a 512-dimensional vector, but for simplicity, let's show everything in 2 dimensions. The most intuitive similarity metric is to use the Euclidean distance between the points. However, this isn't necessarily the best for something like a search engine. Ideally, we should be able to express similarity as a percentage, as in, this image is a 90% match for the search query. Because Euclidean distance can be anywhere between 0 and infinity, there isn't a clean way to map it onto the range 0 to 1. A better approach is to use something called cosine similarity. Treat each embedding as a vector radiating out from the origin. Then calculate the cosine of the angle between the vectors. Since the cosine of the angle between the vectors must be between -1 and 1, we can add 1 and divide by 2 to express the distance as a percentage. And voila! We've now replicated the core functionality of every modern search engine. CLIP forms the basis for the multimodal capabilities of LLMs. It's no surprise that Alec Radford, the lead author on the CLIP paper, was also the lead author on the GPT-1, GPT-2, and Whisper papers. What a stacked resume. Given that CLIP was released in 2021, and FLoC Freeform was released in 2025, I think it's safe to say that whatever FLoC is using, it's probably faster and more accurate than OpenAI's CLIP. This article from Footnote 4a details how FLoC outsources data labeling to the Philippines through Upwork. The example they show indicates that FLoC is gathering training data for object detection. CLIP can get distracted by details from the backgrounds of images. To cut down on false positives, object detection can be used to crop out anything in the image that isn't a person or a vehicle. If there are millions of hours of video footage, it becomes infeasible to search the video frame by frame for every single search query. To speed up the searching process, the video needs to be indexed ahead of time. In other words, how does the system rank the search results without brute forcing the entire database? If it's acceptable to approximate the search results, the system can use a class of algorithms known as approximate nearest neighbor search. Several so-called vector databases have been developed for using these algorithms. ChromaDB and Milvus are open source options, but there's also Zilliz, Pinecone, Weaviate, and Qdrant, not to mention existing databases like MongoDB, Neo4j, and CockroachDB. FLoC appears to be a customer of both Amazon AWS and ClickHouse, which both support vector searches, but it's also possible that FLoC uses a specialized vector database just for freeform. There are thousands of variations of approximate nearest neighbor search algorithms, but I'll explain 2 common ones here. For the sake of simplicity, let's say that the images and search queries are encoded as vectors with 2 dimensions. Given a search query, the goal is to find the x, y points in the dataset that are closest to the query point. One intuitive way to solve this is using a dividing line, like the x-axis, to split the dataset into 2 halves, then only search the half of the dataset that the query point falls in. This is the simplest form of an algorithm called locality-sensitive hashing, or LSH. In this example, LSH cuts the search time in half, but if the query point is near the x-axis, then nearby points on the other side are excluded. There are many ways to attempt to remedy this issue, like using multiple dividing lines or clustering the points, but ultimately they perform poorly on higher dimensional data. Instead of viewing the data as points in a Cartesian plane, They can be viewed as vertices in a vertex and edge graph. From here, vertices that are similar to each other are connected using edges. This data structure is known as a nearest neighbor graph. To run a search query, pick a random vertex in the graph, then traverse to the neighbors that have a smaller distance to the query point. The best performing nearest neighbor graph is known as HNSW, or Hierarchical Navigable Small World. HNSW splits the graph into two layers. One layer is for routing to the correct area, while the other layer is for refinement to home in on the best match. Think of the routing layer like using an airplane to fly to the correct country, and the refinement layer like driving on the local roads to reach the exact location. The details of HNSW are way too complex to explain here, but I figured it was worth mentioning since all the vector databases advertise that they use it. Now that we have a high-level overview of how Flock Freeform works, it's time to build our own. My goal here isn't to replicate Flock's technology stack exactly. If you're looking for how to build a DIY home security system, I'd recommend checking out Frigate, which is a free and open-source network video recorder. It even implements semantic search using Clip. What I'm building is more akin to Google Photos or Apple Photos, both of which allow you to semantically search your photos and videos. In the case of Apple Photos, it even shows you which part of the video matches your search query. I figured it'd be fun for YouTube to build a search engine from scratch and make it run as fast as possible. It might take law enforcement several days to obtain a search warrant, but how long does it take to get the search results after pressing enter? The first decision we have to make is which hardware we want to run on. Most data centers use NVIDIA GPUs to run AI models. The thing is, I don't personally own any NVIDIA GPUs, and I'm not going to spend thousands of dollars buying one. What I do own is a MacBook Pro, and believe it or not, it's actually fairly competitive with NVIDIA when it comes to inference. Since we're going to be taking advantage of many low-level details of the Apple silicon, it makes the most sense to build the app using Swift, which is a native programming language for macOS. I previously attempted to build the app with a cross-platform framework that calls into native code, but that ended up being more effort than it's worth. Plus, it went against the idea of building the highest performance app possible. Now that we've decided on the hardware, we have to decide which Clip model to use. If you didn't know, Apple processors have a special part of the processor known as the Apple Neural Engine, or ANE. It's faster and more power efficient than the GPU for running most AI models. The only way to access it is through a framework called CoreML. Thankfully, Apple developed their own version of Clip called Mobile Clip, and released CoreML versions of the model. Using Xcode, we can benchmark the model and see which parts of the processor it uses. As we can see here, it takes 1.83 milliseconds to run the image encoder on a single image. That means we can index 546 images per second, which is insanely fast. Now that we have our Clip model, our next objective is to figure out the fastest way to decode videos. Videos are made up of intra-coded frames, or iframes, and predicted frames, or pframes. When a video is compressed to reduce file size, iframes are used for frames where significant visual changes occur. Pframes are then computed as a function of the iframes. There are two important consequences of this video compression. First, iframes are the most important frames for understanding the meaning of the video. And second, decoding pframes is slow because they require that we decode the immediately preceding iframes as well. Consequently, instead of running Clip on every single frame of a video, we should only run Clip on the iframes of the video. There's typically only one iframe for every 1 or 2 seconds of video footage, so by skipping over pframes, we make the video processing 30 to 60 times faster. The final problem we have to solve is how to actually find search results in videos. If I search a video for cat on countertop, which frames should be returned in the search results? Longer videos have more frames to match against, which means there's more opportunities for false positives. I couldn't find any descriptions online for how to do this, so I came up with my own algorithm. First, to avoid single-frame false positives, we smooth over the similarity scores using a moving average. Then we z-score the similarity scores amongst each other. Then we find the maximum subarray using Kadane's algorithm. Finally, we average the scores within the subarray. In practice, This algorithm tends to select time ranges that are too large, but for my purposes, it's good enough. Putting it all together, let me introduce to you the Semantic File Explorer. Type in literally anything you want and find exactly the photo or video that you're looking for. There's something I've wanted to do for a while, and now I finally have the chance to do it. You might not know this, but Google and Apple heavily censor their search results to avoid offending people. Flock Freeform also has built-in safeguards for their searches. Hopefully they won't have the same problems that Google had. Anyway, I want to show you how AI actually matches queries against search results without the filters. When I type in Pizza into Apple Photos, it tells me there's no search results. But when I type in pizza into the Semantic File Explorer, it shows me this meat lover's pizza. When I type mouse cat feeder into Apple Photos, it tells me there's no search results. But when I type mouse cat feeder into the Semantic File Explorer, it shows me this video of a mouse running around, and my roommate's cat sleeping on the job. In my previous video, many of you suggested that I look like a Neanderthal. When I type Neanderthal into Apple Photos, it doesn't show any search results. But when I type Neanderthal into the Semantic File Explorer, it turns out you guys were 100% correct. Ooga booga, my friends. If you enjoyed that video, make sure you smash that subscribe button. Check out my Patreon for behind-the-scenes content. Sources are linked in the description, and I'll see you guys next time.